Welcome to part 2 of gas turbine. In the previous module, we covered how gas turbine works, air standard Brayton cycle, manual solution up to here. And in this module, we are going to go over ideal versus actual cycle, qualitative performance prediction, a very important part, and various modifications to gas turbine. And finally, in the solution module, we will solve another problem with verification by test calc. Let's begin with an animation. This is a screenshot of an animation 8A ideal Brayton cycle that we have already covered. In the ideal cycle, air from state 1 is compressed by the compressor isentropically. So the entropy remains constant. 2 to 3, constant pressure heat addition, and 3 to 4, again, is isentropic, entropy remains constant. In an actual cycle, the compressor and turbine are not ideal. We can expect compressor efficiency to be less than 100%, same with turbine efficiency. And even the heat exchanger, where the constant pressure heat addition takes place, the pressure may drop a little bit. To understand how an actual cycle looks like, let's first think of the compressor. So here's the compressor. State 1 and 2 is the exit. So if we apply the entropy equation to the compressor, steady state, no heat transfer, even for an actual cycle these are true, and for an ideal cycle there is no friction. So therefore S1 equals S2, or the isentropic condition is reached. Whereas suppose the compressor is an actual compressor and we call the exit state to be state 3 and apply the entropy equation again on this actual compressor, this time again steady state, no heat transfer, but for an actual compressor we can write S3 equals S1 plus, so what this says is that S3 must be greater than S1 because we know friction is always greater than 0 in an actual compressor. At the best, it can be equal 0 for an ideal compressor. So as you can see, in an actual Brayton cycle, the compressor exit will not be at state 2, it will be at state 3, where state 3 is slightly greater than 1. With this in mind, we can do the same thing for turbine. So the modified cycle will look something like this. 1, again, notice that we are putting 2 different exit states after the compressor. 2 is the ideal one and 3 is the actual one. Instead of drawing 2 different compressors, this is a shorter way. Similarly, for the turbine, notice that there are 2 different exit states. So if you go to the TS diagram, from 1 to 2 is the ideal compressor. 1 to 3, notice S3 is greater than S1, is the actual compressor. And 3 to 4, constant pressure assumption is pretty good even for an actual cycle, so we kept that. 4 to 5 is the ideal turbine, and 4 to 6 is the actual turbine. We know very well how to find state 2 from state 1, for instance. Use isentropic relationship and we can find T2 from T1. So how do we find T3? Well, that's where the compressor efficiency comes in. And what is compressor efficiency? Just to remind you, so efficiency of a compressor is what? Is a smaller amount divided by the bigger amount. The compressor work, the actual compressor work, we expect it to be higher than the ideal compressor work. And that's the definition of compressor efficiency. So what is the ideal work and what is the actual work? Notice the ideal compressor takes the air from 1 to 2 and the actual from 1 to 3. So therefore, it will be m dot, the ideal work is H2 minus H1 and m dot H3 minus H1. So therefore, the compressor efficiency if we use the PG model, so if we know the compressor efficiency and if we know T1, we can find T3. Likewise, the turbine efficiency would be what? This time, the actual work of a turbine will be smaller than the ideal work. Instead of memorizing such a formula, always think an efficiency is less than 1, so therefore the smaller quantity goes on the numerator. So actual work for the turbine, again, the actual turbine goes from 4 to 6. So therefore, the work by the turbine will be four to 6, and the ideal turbine is 4 to 5. And as you can show that the temperature at the exit are connected by the turbine efficiency. So if we know T4, if T4 is given from T4, we can find T5 through isentropic relation. And once we know T5 and turbine efficiency, we can find T6 from the turbine efficiency relationship. So now that we know we can find temperature at 1, 3, 4, 6, we can find the actual turbine work, you can find the actual compressor work, and the analysis follows just like we did the ideal Brayton cycle. When we take up a solution, in the next problem we solve, we'll introduce an efficiency, and these steps will become even clearer. Well, just like we did for reciprocating cycles, we'd like to predict the performance of a gas turbine, how its net power and efficiency and thermal efficiency change as we change certain parameters. So let's start by first comparing a simple Brayton cycle in a TS diagram with a corresponding Carnot cycle. So let me quickly draw a Brayton cycle. And important thing to understand in this cycle is that heat addition takes place at constant pressure and heat rejection also takes place at constant pressure. But the temperature doesn't remain constant, whereas in a Carnot cycle, the big difference is that the cycle look like a rectangle. Both heat addition and rejection takes place at constant temperature, and heat addition temperature is TH, TC, and that gives us an efficiency, thermal efficiency of the Carnot cycle to be 1 minus Tc over Th. Now, to understand the qualitative performance, first we recognize that the net area inside is proportional to the net power. So, just by looking at how much area is included in a cycle, if we compare a cycle with another one, if you find the net area is bigger, we know the power output will be higher. To compare the efficiency, we fall back on the Carnot analogy. Even though in the Brayton cycle the heat addition doesn't take place at constant temperature, we can say, maybe heat addition takes place at an average, on an effective temperature of Th bar, and heat rejection takes place at some effective temperature of Tc bar. Then the thermal efficiency of the Brayton cycle will be something like 1 minus, I shouldn't say exactly equals, approximately Tc bar over Th bar. See if that makes sense to you. For a Carnot cycle, we know this is an exact formula, 1 minus Tc over Th. Th is where Q dot in occurs, Tc is where Q dot out occurs in a Carnot cycle. Whereas in a Brayton cycle, Q in occurs at a variable temperature from 2 to 3, and we are saying maybe there's an effective average temperature, Th bar. So our goal would be, whenever we compare, we modify a Brayton cycle, we'd like to see how Th bar or Tc bar changes. Suppose we could increase Th bar. Can you see that? The thermal efficiency of both Carnot engine and the Brayton cycle will go up, because if Th bar goes up, this fraction will go down and efficiency therefore will go up. So let's take a couple of what if scenarios. We'll think it out. So let's again draw a Brayton cycle, but this time actually this line will be something different. Okay, so suppose this is our base cycle, a ideal Brayton cycle, and the what if experiment we want to do, that what will happen if we increase the compression ratio without changing the maximum temperature. So this is the maximum temperature of the cycle. So let me first draw the heat addition and heat rejection part on this cycle. And our goal is to see what will happen if the compression ratio is now increased without changing the maximum temperature. This is the Tmax of the cycle, right? So we'll modify the cycle using a different color, let's say blue. So notice state 1 hasn't changed, but compression ratio has increased. So obviously our cycle will extend up to here, let's call it 2 prime. And then the constant pressure heat addition will take place along similar line, but we cannot exceed Tmax. So our 3 prime will be somewhere here, and then isentropic expansion in the turbine will bring us back to constant pressure line. So 1 prime, 2 prime, 3 prime, 4 prime is our modified cycle. Heat addition takes place here, and heat rejection takes place from 1 to 4 prime. So if we compare the two efficiencies, efficiency of the red cycle is 1 minus Tc bar over Th bar. So if we want to spot them here, Tc bar will be, let's say, somewhere here, and Th bar is somewhere there. Whereas for the blue cycle, this will be somewhere where will be the Th bar is, and this is, see, heat rejection is from 1 to 4 prime, so the average temperature of heat rejection is somewhere here. As you can see, Th bar has gone up and Tc bar has gone down, both of which tend to increase efficiency. So what conclusion we draw? That if you raise the compression ratio, the efficiency is going to increase, and that's without solving the problem by hand. If somebody asks, how will the net power change? Well, we know the net power is what? M dot times net power from one cycle. However, it is difficult to say if the blue area included inside the blue cycle is bigger than the red area. So our conclusion would be, well, we don't know how the net power will change. But imagine if we keep on increasing the compression ratio, what is the limit? If I drew the limiting cycle in green, you can see that I can keep increasing the compression ratio, and the cycle will finally look like very, very thin, and the area will go to 0 gradually. So we know for sure that if the compression ratio is really, really high, it's not that good. Even though the efficiency will be very high, the net power will go towards 0. Okay, so let's do another thought experiment. Once again, I have drawn a base Brayton cycle, 1, 2, 3, 4. You can see the heat addition takes place from 2 to 3 at an effective temperature of Th bar, and heat rejection at Tc bar. So the efficiency of this red cycle will be given by 1 minus Tc bar divided by Th bar. Now suppose we are increasing the maximum temperature allowable in the cycle. So the turbine inlet temperature, which is at 3, we have designed a new turbine that can withstand higher temperature, and let's draw the modified cycle in blue. So that means we can keep heating the air from 2 at constant pressure way to, let's say, 3 prime. So we have considerably raised the maximum temperature. So how will the new cycle look like? At 3 prime, again, the turbine is isentropic. It will go down vertically, and it will meet the constant pressure line at 4 prime. So 1, 2, 3 prime, 4 prime will be our new cycle. So how does that affect the efficiency? We realize the new cycle, when the temperature increases from 2 to 3 prime, is our heat addition. So the effective temperature of heat addition is raised to Th bar. But look, what happened to effective temperature of heat rejection? That's also kind of raised to Tc bar. So thermal efficiency, which is 1 minus Tc bar divided by Th bar. This is good news, Th bar is increased, but so is Tc bar. So you can see that you cannot say for sure if thermal efficiency is now higher or lower or about the same. So our conclusion about thermal efficiency is inconclusive, but we can say for sure that when the maximum temperature is raised, the net area is increased by a significant amount. So there will be more power output from the power plant. However, thermal efficiency, we don't know for sure. Notice that also the exhaust temperature is raised if the maximum temperature is raised. So keep that in mind when we modify the gas turbine in different ways in our next segment. Okay, we'll discuss the first modification to a simple Brayton cycle. This is called the reheat cycle. Again, this is a screenshot from the animation reheat. So let's begin by looking at how this cycle differs from a standard Brayton cycle. State 1 is the same, atmospheric air at 100 kPa. It's compressed, let's say, by a factor of 16, let's say 1600 kPa isentropically, so nothing different so far. From 2 to 3, constant temperature heat addition, which at state 3, temperature is higher, the pressure will be remaining the same, 1600 kPa. And the average temperature of heat addition is somewhere between 2 to 3. But now, in a normal Brayton cycle, in a simple Brayton cycle from 3, we go all the way down to state 4 prime, right? Which will be a single turbine expanding from 1600 kPa to 100 kPa. But what we do here is that we break the turbine into two different stages, from 1600 to, let's say, 400 kPa, and then from 400 to 100 kPa. So when it goes from 1600 kPa to 400 kPa, the turbine is producing power 3 to 4, and then the gas that is coming out of the turbine is at a lower temperature, obviously. As the gas expands, you know, temperature drops, pressure drops isentropically. And from state 4, we again add heat, raising the temperature back to the maximum temperature of the cycle. So what happens is that from state 5 again, it expands through the isentropic turbine. As you can see, what happened as a result, we have just added an extra area to the TS diagram. That means the power output will be increased significantly. Remember, we could just raise the temperature at the exit of the combustion chamber to raise the power output. However, turbine material may not withstand a very, very high temperature. So we may have to operate a gas turbine under some constraint that you can never cross Tmax for material consideration. So reheat is a very nice way in which we can expand the net area, which means the power of the cycle, without raising the maximum temperature. How will it affect the thermal efficiency? Well, by now, you can see almost that thermal efficiency 1 minus Tc bar over Th bar. First of all, because of the additional heating, which happens at a very high temperature, you can see the Th bar will have a tendency to go up, because the additional heating is carried out at a much higher temperature, much higher average temperature than the original heating, 2 to 3. However, the heat rejection now takes place from 6 to 1 as opposed to 4 prime to 1. So therefore, the heat rejection temperature has also gone up. So we cannot say for sure a reheat is going to help us with efficiency, but it sure helps us with the net output of the turbine. Another important modification to gas turbine is regeneration. This is a screenshot from the animation module. And let's explain what's going on here. Regeneration means taking heat from one part of the cycle and putting it into another without affecting the external heat addition or external heat rejection process. So at state 1, we have atmospheric air, which is compressed isentropically by the compressor, and then the compressed air is receiving heat from the exhaust gas of the turbine. The turbine exhaust is routed through this heat exchanger, and as you can see, the turbine exhaust is supplying the heat to heat up the compressed air. As a result, the effective heat addition temperature is increased and effective heat rejection temperature is decreased. So you can imagine what will happen to the thermal efficiency with effective temperature of heat addition increasing and Tc bar decreasing. Thermal efficiency goes up in regenerative cycle. Let's explain the different states on the TS diagram, and that will bring out the definition of the regeneration efficiency. Well, from state 2, your goal is to heat up the air as much as possible, and we know the turbine exhaust is at temperature 4. So therefore, at the most, you can go from state 2 to state 5. That will be the ideal. State 5 will be the ideal exit condition for the compressed air. So if you want to define an efficiency, the ideal temperature rise is what? T5 minus T2, and T5 being T4. So this is in the denominator. And in reality, probably the regenerator is not so effective, so it raises the temperature from 2 to 6. So T6 minus T2 is the actual rise in temperature, and T4 minus T2 is the maximum that is possible, and that is known as the effectiveness of the regenerator. So if the effectiveness is given, we can calculate what would be T6. So in an analysis, probably we'll know T1 is given. We can find T2 isentropically. T3 is probably given. So therefore, isentropically, we can find T4. And if we know T4 and we know T2, and therefore, we can find T6 from epsilon. Again, it will become clear when we solve the problem. As far as the net work goes, look, the net area inside is not changed at all by regeneration. So the regeneration doesn't affect net work, net power. However, it increases efficiency tremendously because the external heat addition takes place, notice, from state 6 to 3. In an original cycle, it would have been taking place from 2 to 3. So the TH bar is increased. In the original cycle, heat rejection would be taking place from 4 to 1. But now, thanks to regeneration, heat rejection takes place from 8 to 1. How do you find state 8? That can be obtained from a simple energy balance in the regeneration system. The heat rejection is given by m dot H4 minus H8. That's the heat rejected by the hot gas, and m dot H6 minus H2 is the heat gained by the compressed air. So if we equate the two, you can obtain the state 8 for a regenerative cycle. Recall that when you did reheat, the net power increased, but the efficiency did not change. Whereas in regeneration, the efficiency is increased, but the net power doesn't change. If we combine reheat with regeneration, that's an ideal combination because, as you can see, because of reheat, we have this extra area, which means more power, and because of regeneration, TH bar has gone up. Heat addition is taking place from 7 to 3 and 4 to 5, whereas heat rejection is taking place at 8 to 1. And for the same reason we have been talking repeatedly, if we can increase the TH bar and reduce TC bar, efficiency goes up. I would say go over the animation carefully, and you can see how each state can be evaluated from the knowledge you already have. We'll solve a problem, a quite complex problem next, and that will kind of put it all together.